All right, so I've just noticed that in our method 1, here I canceled the 2 with the 2, so the x should be in the numerator, but I put 2 instead of x. That is supposed to be an x. Then, when we do dy dx at x equals 2, we replace the x with 2, and we get everything else is the same. That 2 is supposed to be an x. I don't know whether I said x or 2, but I wrote a 2, which really threw me off in the next video. All right, so here we go. Now we're going to do method 3, implicit differentiation. All right, and that's what we're actually that's our goal for today. What we're learning today is a technique that allows you to easily find derivatives when it's not easy to solve for y. This one, by the way, relatively easy to solve for y. We're going to use this method in situations where you cannot solve for y. So it's going to be very useful for that kind of thing. Okay, so here's how it works. What you do is you take the derivative with respect to x on both sides of the equation. All right, so derivative with respect to x is 2x. Derivative with respect to x of x squared is 2x, so that's fine. Now, how are we going to do derivative of y squared, but with respect to x? So what this means is we need x to be the dependent variable, but x is not the dependent variable here. So what you have to think of is that this y squared is really y of x squared, where the y of x is an inside function. And you use chain rule. So you do the derivative of the outside function, bringing the, using the power rule, but then you have to multiply times the derivative of the inside function being y of x. All right, now here's the fun thing. I don't know what the derivative of y is, but I don't know what the derivative of y of x is, but I can call it dy dx and then keep working from there. Right, this derivative of y with respect to x is dy dx. That's what we mean by dy dx. So that's your g prime right there. And then for 16, the derivative with respect to x of 16 is 0. Okay, so now here's the tricky thing. I don't know what the dy dx is, but it's in my equation and I solve for it. So what I do is I'll do minus 2x on both sides, minus 2x, minus 2x. So then I get 2y dy dx equals negative 2x. And then I dissolve, I divide both, dissolve is what's happening to my brain right now. I divide both sides by 2y, and I get dy dx equals negative 2x over 2y, which I can simplify as negative x over y. Now, the derivative and the process looks really different, but did I get the same result that I had here? So actually you did, if you remember that from here, y is equal to square root 16 minus x squared. So this square root 16 minus x squared here is y, and that corresponds to our y here. So the derivative is negative x over y. So we get this derivative this way. And then sort of something that's unique about it is we've expressed the derivative, but not just in terms of x, it's in terms of x and y. So that's sort of the price you pay for doing the derivative without solving for y, is your result has x and y in it. But it's often easy to get the x and y. So we know at x equals 2, so then here's the thing. We have to find out what y is. X squared plus y squared equals 16. 4 plus y squared equals 16. Y squared equals 12. Y equals plus or minus square root of 12, which is plus or minus 2 square root 3. And because we're in the first quadrant, right, first quadrant, therefore we're going to choose the positive 2 square root 3 for y. All right, then we can plug our x and our y in here. So the derivative, and so now look how useful this notation is. I can say the derivative evaluated at x equals 2, y equals 2 square root 3. So I can use this notation with a point down here with an x and a y. So that means I'm going to take this derivative and I'm going to plug in x equals 2 and y equals 2 square root 3. Okay, and so that's going to give me negative 2 over 2 square root 3. And once again, I get negative 1 over square root 3, which is negative square root 3 over 3. And that's the same result we got every time that we did this. No matter how you slice this, it comes up peanuts, and the peanuts are negative square root 3 over 3. All right, so this is the basic process. So what I want to do is sort of dissect that process and go through some more examples. But essentially it's like this. Step 1 is the derivative with respect to x on both sides. Maybe we'll make these steps red. Step 2, we are going to What we really did was get everything that was not dy dx to the right. So we put dy dx on the left, anything that's not dy dx to the right. All right, step 3 is we're going to divide to solve for dy dx. That's pretty much it. Then we're done. Simplify if possible. All right, so we're doing derivative of both sides. The dy dx's stay left, the non-dy dx's stay right, and then we divide to solve for dy dx. Sometimes you have to do a factoring step first. We will see these in the next examples.